Lambda expressions. What are they? Lambdas are best thought of as small pieces of code that act like functions, but are not designed for reuse and therefore they don't warrant a proper named function declaration and definition. Rather, you would include them in your code inline, where and when you want them to execute. Lambdas have a strange syntax, so one of the challenges in understanding and learning to use lambdas is in getting familiar with the syntax. The simplest of all lambdas consists of a capture clause, the symbol of which is a pair of square brackets, followed by the body, delimited by curly braces. And this is where the program statements doing the actual work are. In this example, the capture clause is empty, and the lambda just sends a message, a string of characters, to the standard output. This lambda expression is assigned to a variable, and in order to execute it, the function call operator is placed after the variable. The step of assigning the lambda expression to a variable can be omitted if we simply write the function call operator after the lambda itself. Before I run this example, I just want to point out that the compiler actually turns the lambda expression into a function object, like the one here, except the name wouldn't be advice, but some weird auto-generated string of characters. So here is the output. The first line is from this statement here. The second is from this, and the third is from the execution of the function object. So that was a very simple lambda expression. Now let's see what else we can do with lambdas. Lambda expressions can also take parameters and return values in a similar manner as functions do. Parameters are listed within brackets after the capture clause, but as we saw earlier, if the lambda expression doesn't take any parameters, then those brackets are not needed, although you might see examples with empty brackets. The type of the return value is written after an arrow, as you see here. But this is also optional if the compiler can deduce the type of the return value from the code. This lambda expression takes two numbers as input, adds them together, and returns the sum. Now, seeing that this lambda expression returns an integer, you might be led to believe that the variable adder, declared as type auto, resolves to be an integer, but that's not the case. Adder is like a function. On the next line, the variable sum is initialized with the result of the lambda's execution. The same example can be written out slightly differently without assigning the lambda expression to a variable. If we append the function call operator with the two integer arguments to the end of the lambda expression, then we effectively execute the lambda, and the result is assigned to the sum variable. Once again, the type of the highlighted code, which is the same as here, is the function itself. Together with the function execution operator, the type is an integer. The adder lambda expression is equivalent to this function object. Notice that the function execution operator is declared constant, since it does not modify the values of x and y. The next thing I want to look at is the capture clause. This is the most intriguing part of the lambda expression. It is called the capture clause because it enables the lambda expression to access or capture variables from the surrounding scope. In these examples, the surrounding scope is the main function. I declared and initialized two variables here, and using them in this lambda expression here. As you can see, this lambda expression is, in turn, used to initialize the variable another adder, which is, you guessed right, a lambda expression. And that lambda expression is executed here. If these two lines were converted into a class, it would look like this. The captured variables become data members of the class. I don't know if you can see the similarity, but when an object of the another adder class is created and initialized, it's like here. And this is where the result is printed. We are not yet done with capturing variables, because there's a lot more to it and it can get rather tricky. In the previous example, we listed the names of the variables we wanted to capture inside the square brackets. Those variables were captured by value, which is the default. We can make it explicit by placing an equal sign within those brackets. Not listing any variables after the equal sign doesn't mean that we are not capturing any of them. In fact, it means the exact opposite. It means the lambda expression has access to all of them from the surrounding scope, but only by value. And that is why this first lambda expression will not compile, because it tries to increment the value of I1. In the next one, the ampersand plays a similar role as the equal sign, except it means all variables are captured by reference, unless specified otherwise. Here, the variable I2 is the exception. It is captured by value. In the next example, if it surprises you that sum is equal to 4 instead of 5, just observe that I2 is incremented after the sum is calculated. Lastly, on this line, I have a lambda expression with a capture clause like a Christmas tree to make it more interesting. Sum is captured by reference since we are going to assign to it. I1 and I2 are captured by value. Extra is a local variable initialized to 7 and it is a constant. And then another extra is a reference to I1. Can you guess what the values of I1, I2 and sum are going to be? If we insert the values of I1, I2 and the rest into the equation down here, shouldn't we get 12? Think about it. The reason we get 11 is that the I1 here is 0. Another extra referred to and incremented the I1 variable in the outside scope, which is then printed here. Can it get any trickier? Let's see. In this lambda expression, the variables sum and I2 are captured by value, so we are not able to change them in the body of the lambda expression. But there is a way around that by using the keyword mutable. As you can see, I2 is incremented and sum is assigned a value. Still inside the lambda expression, I2 and sum are printed. There is also a print statement outside the lambda expression. Now let's see what we get. Wow, vastly different results. It is because although mutable permits change to those variables, that change takes place on a copy, not on the original variables in the outside scope. Still on the same topic, here is an example that is different in a subtle way. The lambda expression is declared on these lines. It captures a Boolean variable from the surrounding scope by reference. It is executed down here after the Boolean variable response has been reset to false. If I run this program, then, as you would expect, the false branch of the if statement was executed. Now, would that change if the response variable was captured by value? The lambda expression will still be executed after the response variable is set to false. This time we got a different result. So what is the conclusion we can draw from this? I guess it is that lie detectors are unreliable. But seriously, what happens here is that when the variable or variables are captured by value, then the lambda expression is evaluated at the time it is compiled, and it is set in stone, so to speak, after that. There is this const_exp keyword one could insert in here to emphasize this fact. This indicates to the compiler that this expression as written can be evaluated at compile time, and that allows certain optimizations to take place. My next example demonstrates what happens when a global variable is captured by the lambda expression. The global variable g_a number is declared up here, and its value is 100. I also have a local variable which is initialized to 9. Inside the lambda expression, a number is added to the global variable. Can we do that? Notice that the equal sign in the capture clause means we are capturing everything by value. So technically, the code in the lambda expression is not allowed to modify the captured variables. Now let's see what happens. Well, we do get a result, and it's weird. Not only was the lambda expression able to change the value of the global variable inside the body of the lambda, but that change turned out to be permanent. It affected the global variable in its global scope. That is potentially dangerous, so extra care should be taken. The use of global variables is not recommended anyway. If you can still stay with me, my next topic is nesting lambda expressions. Here we have this lambda expression within this lambda expression, and when executed, the result is assigned to the total variable. Remember that these are function execution operators, each with an integer argument. Now let's do this. Stop the video now and try to figure out what the result will be. It says 13. Let me explain why by breaking up this entire expression into its constituents. The important thing is to correctly identify the various elements. The inside or nested lambda expression is this. It consists of the capture clause, which is empty, the parameter list, and the body of the lambda within curly braces. This here is a function call operator that evaluates the lambda. and 3 is added to the result before it is returned. Now I will give these program statements a name, let's say final_result, and rewrite what we have here, like this. Then it is easy to see that the x parameter takes on the value 5, which comes in as the argument in the function call operator. So now we know that x is 5. The body of the outside lambda, that I called final_result, can be written out like this, and then in a similar manner as before, we can determine that the parameter y takes on the value of x, which, as we now know, is 5. So y is also equal to 5. The calculation of final_result is straightforward now, and it is the result assigned to the variable called total. Now I want to approach the same nested lambdas example from a different angle. As I said at the beginning, a lambda is very much like a function. It accepts input either by capturing variables from the surrounding scope or via parameters, executes program statements, and might return a result. I said result, but the return value doesn't have to be the result of a calculation. It can also be, and this is what concerns us here, a function, or another lambda acting like a function. What you see here is a lambda expression returning a function, which is itself a lambda expression originally. The signature of the function should match the lambda expression. So this lambda has an integer input parameter and returns an integer, which matches the function declaration here. I don't know if you can read it because the type is very small, but this path_result_calculator variable is a function, or lambda, as I can use these terms interchangeably. It has an integer parameter and returns a function. I can now create another lambda that takes a function as one of its input parameters and an integer as another parameter, and returns the result of executing that function. When I put the two together, nesting one lambda expression inside another and supplying the same arguments as above, then I have basically rewritten the same expression as this one in a different format. As you can see, the results are the same. Notice that f is a reference to a function, and it is a constant reference. So f cannot be changed to refer to some other function. The program would work even if f wasn't neither a reference nor a constant, but this here is the right way of declaring this parameter, both for efficiency and safety. The examples we've looked at so far have been rather simplistic. Let's look at a more complex example, one that resembles a real-life scenario a little closer. What I've done here, I created this audio device class. Audio device takes audio data, say from a file, as its input, applies some processing to it, and sends it off to the speakers. The audio data comes in a vector, and for simplicity, I put that into the object constructor. The data can take various forms, and that is why the vector is declared with a template type for its contents rather than a specific type. The processing is implemented in a function, and it takes place in 3 steps. Each one of those processing steps is the execution of a lambda expression. Let's examine them one by one. At first, the sound gets amplified by some amount. The amplification amount is hard-coded here. That's not important. What is important is that the amplification amount comes in as the value of this input parameter to the lambda. In the lambda body, each sample in the incoming audio data is multiplied by the amplification amount. The type of the samples will be automatically deduced by the compiler. So as you can see, this is a possible way to write generic lambda expressions. This lambda captures a pointer to the audio device object in which it appears. It is necessary because the lambda needs access to this m_data vector, which is a member of the audio device object. The lambda on the next line also iterates over the samples in the audio data, but this time it applies a function to each sample. That function comes in as an argument of process and play, and the lambda gains access to it because it captures a pointer to the object, as we've seen before. Now, why do I need this ampersand here and not here? Let's see what happens when I delete this ampersand. See, I either have to explicitly list every variable I want to capture or specify a default capture mode, which can either be by reference, using an ampersand, or by value, the symbol of which is an equal sign. The third lambda expression simply outputs the value of each sample. Here, samples are converted to strings, but for the sake of playing with this audio device idea, I call it converting to an analog signal. Before I run this example, there are two more things we need to look at. What is a sample? In this example, a sample can be one of two things. It can either be a floating point number, which is very common in audio processing, or an instance of this class I created here. Internally, it's just a string, but since externally it is a user-defined object, certain operators had to be overloaded for this class to be used in calculations. These include the combined multiplication and assignment operator, the assignment operator, and the stream insertion operator. Also, this Boolean operator, which is used elsewhere, we will meet it in context shortly. The reason the stream insertion operator is overloaded as a global function, unlike the others, which are methods of the class, is that the stream variable appears on the left-hand side of the operator. This is just a rule in operator overloading. The other thing I need to talk about is this post-process function, which is, in fact, a lambda expression I call limiter. It looks at each sample and does not allow the sample's value to go beyond a certain limit. Here is the Boolean operator we had to overload in the sample class. So let's see what happens here. A vector of floats is created using an initializer list. That is our audio data. We also need data where the data items are sample objects. And here is a handy use of a lambda expression. Instead of writing code to create each sample one by one, we can just let this lambda do the work. Having created two sets of samples, we can let an audio device process each one of them. Device 1 processes the floating point data. Device 2 processes the samples data. The limiter, which is a lambda, is passed in as the argument of the process and play function. As you can see, the limiter was busy at work in two instances. The default formatting for floats and strings is different, but the values are the same. I hope you got some valuable insights into how lambdas work and where and how you could use them to your advantage. If something is not clear and needs further explanation, please let me know in the comments below. Also, check out my other videos on my YouTube channel. Thanks for watching. Bye.